Hello, welcome. We are glad that you're here. Sit back, relax, on your couch, put your headphones on, because what you're about to watch is going to take you on a journey through the universe like you've never seen before. Let's talk about something that keeps humanity awake at night. The universe. It's massive, it's ancient, and it refuses to give up all its secrets. Why are we here? What's holding galaxies together? What's pushing them apart? And what happened before time itself began ticking? These aren't just scientific questions, they're human questions. The kind you feel late at night when you stare up at the stars. Look around. Billions of galaxies. Each has billions of stars, and maybe billions of planets that could host life. But here's the twist. The more we discover, the less we seem to know. Dark matter, dark energy, black holes, the Big Bang. They're all hints. Hints that reality is stranger than our imagination. Think about it. We live on a tiny rock, orbiting an ordinary star, in a random corner of the Milky Way. Yet, somehow, we have the brains to ask these cosmic questions. That's the real magic. The universe isn't just out there. It's in here, in us. We are stardust trying to understand the stars. So, why does the cosmos keep us awake? Because deep down, we know the answers matter. They tell us where we came from, where we're going, and, maybe, why we exist at all. This series is a journey, 40 sections, 40 mysteries. Each one is more mind-bending than the last. We'll talk about dark matter, we'll wrestle with time, we'll chase aliens across the galaxy, and we'll even ask if this universe is the only one. By the end, you might not have all the answers, but you'll see the universe with new eyes. Eyes wide open to wonder. So, buckle up. We're diving into the deepest mystery ever written. The story of everything, and you're a part of it. If that excites you, stick around. Hit that subscribe button. Join us on this cosmic adventure. Because the biggest mysteries of the universe are just getting started. Every answer we find in the cosmos sparks a dozen new questions. It's never ending. We thought Earth was the center. Wrong. We thought the Milky Way was the entire universe. Wrong again. Every discovery tears open another frontier. That's the unknown. It doesn't shrink. It grows. The more we learn, the more mysterious the universe becomes. Look at dark matter. We can't see it. We can't touch it. Yet it shapes galaxies. Without it, nothing we see would even exist. We know it's there, but we don't know what it is. Then there's dark energy. Even stranger. It's pushing the universe apart. Galaxies are racing away faster and faster. Why? No one knows. Black holes? The most terrifying mysteries of all. We thought nothing could escape gravity, but black holes trap even light. And, at their cores, physics breaks. Space, time, reality itself, all shredded. And just when we think we're getting close, the universe laughs, throws us another curveball. Take exoplanets. We dreamed of other worlds. Now, we've found thousands, but instead of answers, more questions. How many can host life? What kind of life? Are we alone? Every telescope, every mission, every equation points to something bigger, something beyond what we know. The frontier isn't just out there, it's inside our minds. Our ideas about reality are constantly tested. Are space and time fixed? Or are they illusions? Is the universe infinite, or does it end? And if it ends, what's outside? Science doesn't shut the door, it opens it wider. That's the thrill, that's the fear. We're chasing answers into the dark. Imagine this, a puzzle with no edges. Every piece you place makes the puzzle bigger. That's the universe, that's the frontier. So, when people say we're close to figuring it all out, they're wrong. We're just getting started, and the mysteries waiting for us, they'll change everything we think we know. The universe doesn't hand us answers. It whispers in riddles, half-truths, clues scattered across the sky. Science exists because of that. Not because we already know, but because we don't. Every mystery is a spark. Why does the sun rise? Why do stars move? Why does an apple fall? Simple questions. But each one opened the door to a revolution. Newton saw gravity in that falling apple. Einstein saw time bending around stars. Hubble saw galaxies drifting apart. Each discovery began with a riddle. And every time we solved one, the universe slipped another onto the table. Black holes were once a theory. Now we've seen their shadow. But the closer we look, the stranger they get. Are they gateways? Do they destroy information? We still don't know. Quantum mechanics? It works better than anything we've ever built. Yet, it makes no sense. Particles here, but also there. Alive and dead. Everything certain and uncertain at the same time. That's not an answer. That's a cosmic joke. Dark matter and dark energy? Together, they make up 95% of the universe. The stuff we actually understand, stars, planets, people, just 5%. It's like reading a book, when most of the pages are missing. But that's the point. The riddle is the engine. The not knowing is the fuel. If we had all the answers, science would stop, curiosity would fade, exploration would end. Instead, every mystery drives us forward. Every puzzle pulls us deeper. It's a conversation across time. We ask, the universe replies, but never directly. It leaves hints, a wobble in a star's light, a flash of gamma rays, a signal in the background hum of the cosmos. And we chase those hints, generation after generation, building tools, building theories, building hope. The riddles remind us of something important. We're small. We don't command the universe. We listen to it, interpret it, try to read its language. And maybe, just maybe, that's the real mystery. That we, fragile creatures on a tiny planet, can even hear the riddle at all. The cosmos could have stayed silent, but it didn't. It gave us puzzles, and the courage to chase them. So, when we stare into the night sky, we're not just seeing stars, we're seeing questions. Questions written in light, in gravity, in time itself. And that's why science will never end. Because the universe always writes in riddles. Every time we look up, one thought keeps echoing. What's the single most mysterious thing in the universe? Is it black holes? Those monsters that bend time, swallow light, and warp reality itself? They're terrifying and fascinating. Or is it dark matter, the invisible skeleton of the cosmos? It doesn't shine, it doesn't glow, but it holds galaxies together like an unseen hand. We've mapped its effects, but never touched it, never seen it directly. Maybe it's dark energy. That nameless force stretches the fabric of the universe, accelerating expansion, making galaxies race apart faster and faster. It's everywhere. It dominates everything. And yet, it's a blank page in physics. But maybe the biggest mystery isn't out there. Maybe it's right here. Consciousness. The universe is aware of itself. Atoms are arranging into neurons. Neurons are arranging into thoughts. Thoughts daring to ask, what's the most mysterious thing in the universe? That's wild. Some would say it's the beginning itself. The Big Bang. Why did it happen? What was before it? Was there a before? We don't know. We may never know. Others argue it's the end. Heat, death, big rip, collapse. What's the final fate of everything? That's a mystery hanging over all of us. Here's the truth. You can't crown just one, because every answer opens another door. The single most mysterious thing isn't a thing at all. It's the cycle, the endless chain of questions. We thought Earth was the center. Wrong. We thought the Milky Way was the universe. Wrong again. We thought we understood matter. Then came dark matter. We thought expansion was slowing. Then came dark energy. Each time we solved a puzzle, the universe laughed and handed us a bigger one. So maybe the most mysterious thing is the universe itself. Not a piece of it, not a part of it, the whole. Because it's not just vast, it's structured, it's creative, it's alive with questions. And here's the twist. The riddle only exists because we can ask it. If there were no minds, no curiosity, no wonder, would the universe even be mysterious? So, the biggest mystery might be the bond between us and the cosmos. Why we're here? Why can we think? Why can we dream about stars billions of light years away? The big question isn't just what's the most mysterious thing, it's why are we allowed to ask in the first place? And that's where the real magic lives. Because no matter how far we reach, no matter how many galaxies we map, the ultimate mystery will always stare back. Us. Here, now, asking the question. Galaxies spin way too fast. By the rules of physics, they should be flying apart. Stars should scatter into the void, but they don't. Something's holding them together. Something massive. Something invisible. We call it dark matter. It's not made of atoms, not light, not gas, not dust. It doesn't glow, it doesn't absorb, it doesn't interact with us the way normal matter does. And yet, it's everywhere. It outweighs normal matter 6 to 1. For every star, every planet, every molecule of you and me, there's 6 times more of this invisible shadow stuff. We didn't stumble on it by choice. We were forced into it. Astronomers noticed galaxies behaving strangely, spirals spinning without falling apart, clusters of galaxies bound tighter than gravity should allow. The math didn't add up. The universe was cheating. Enter Fritz Zwicky, 1930s, a bold astronomer with a knack for ruffling feathers. He looked at galaxy clusters and said, "There's missing mass. Something unseen is holding this together." The community laughed. For decades, they ignored him, but he was right. Now, dark matter is one of the pillars of modern cosmology. Still, we have no clue what it actually is. Some think it's exotic particles, WIMPs, axions, sterile neutrinos. Others whisper about hidden dimensions, or modifications to gravity itself. We build detectors deep underground. We smash particles in giant colliders. We stare at the sky through gravitational lensing. The warping of light as it bends around invisible clumps, all to catch a ghost that refuses to be caught. Here's the kicker. Without dark matter, galaxies wouldn't exist. Stars wouldn't cluster. Planets wouldn't form. Life wouldn't emerge. You and I wouldn't be here. Dark matter is the silent architect of the cosmos. The unseen hand is painting galaxies across space, the framework on which everything hangs. And yet, it's still a shadow, a name without a face. Think about that. We've mapped the universe. We've measured its age. We've seen galaxies billions of light years away. But we still don't know what most of it is made of. Every night, you look at the stars. But the real story? It is hidden in the dark. Dark matter doesn't just raise questions about physics. It raises questions about reality itself. If most of the universe is invisible, what else are we missing? What deeper layers lie just beyond our senses? We call it a shadow, but maybe, one day, we'll learn it's not a shadow at all. Maybe it's the scaffolding of creation. Maybe it's the bridge to new physics. Maybe it's the clue that rewrites everything. Until then, it keeps its secrets. And galaxies keep spinning, defying the odds. Thanks to the invisible glue, dark matter's shadow, everywhere and nowhere. For decades, scientists thought the universe's expansion was slowing down. Gravity should be pulling everything back. Galaxies tugging on galaxies. Clusters collapsing. The cosmos is slowing to a crawl. But the universe had other plans. In the late 1990s, astronomers peered into deep space. They measured distant supernovae stellar explosions, so bright they outshine galaxies. Perfect cosmic yardsticks. And the results? Jaw-dropping. The universe wasn't slowing down. It was speeding up. Something unseen was pushing galaxies apart, stretching space faster and faster. A mysterious pressure woven into the fabric of reality itself. We call it dark energy. And here's the crazy part. Dark energy makes up nearly 70% of the universe, the majority of reality, but we don't know what it is. It doesn't matter. Not radiation, not anything we can touch, hold, or see. It's an invisible force with negative pressure. Instead of pulling, it pushes. Instead of binding, it rips apart. Imagine space itself as an elastic sheet. Dark energy isn't just stretching it, it's accelerating the stretch. Every second, galaxies drift farther away. The farther they are, the faster they run, until, someday, they'll disappear from view entirely. Future astronomers might look into the sky and see only a handful of stars. The universe beyond is erased by expansion. Dark energy is stealing the cosmos, piece by piece. So what is it? Some say it's the cosmological constant, the same fudge factor Einstein once called his biggest blunder. A built-in property of space, tiny but relentless. Others argue it's a dynamic field, like a cosmic fluid, evolving over time. And the boldest theories? They suggest new physics entirely, unknown forces, hidden dimensions, a multiverse leaking into ours. Whatever it is, it's unstoppable, and it decides the universe's fate. If dark energy stays constant, galaxies will keep drifting apart forever. Stars will die, matter will fade, heat death will claim the cosmos. If dark energy grows stronger, the big rip awaits. First galaxies torn apart, then solar systems, planets, atoms themselves ripped to shreds. If dark energy weakens or flips sign, gravity might win. The universe could collapse into a fiery big crunch. Every scenario hinges on dark energy, and right now, we don't even know what it's made of. Think about that. The biggest component of the universe, the master of its destiny, and we can't even describe it. Dark matter holds things together. Dark energy blows them apart. One builds, the other destroys, and in between, we exist on a fragile timeline, balanced between creation and annihilation. Dark energy's push isn't just a mystery, it's the greatest cliffhanger in cosmic history. Empty space, nothingness, a void, at least that's what we imagine. But physics says there is no such thing as true emptiness. The vacuum isn't empty, it's buzzing, foaming, seething with invisible energy. Particles pop in and out of existence, virtual sparks flashing and vanishing in trillionths of a second, tiny fluctuations rippling through space. It's called vacuum energy. Quantum physics insists it must be there. Every field, every particle contributes to it. Add it all up, and you get a staggering number. The predicted energy of empty space is 10 quadrillion times larger than what we actually observe. That's not a typo. That's a number so absurd it breaks the imagination. A 1 followed by 120 zeros. The biggest mismatch between theory and observation in all of science. Physicists call it the vacuum catastrophe. If the math were right, the universe would have torn itself apart instantly. It would have inflated into oblivion the moment it was born. No galaxies, no stars, no you, no me. Clearly, something's wrong. But what? Did we miscalculate? Are we missing hidden laws that cancel out the energy? Or is there a delicate balance, a cosmic fine-tuning, where positive and negative contributions nearly erase each other, leaving behind just enough vacuum energy to power cosmic expansion? That just enough is what we call dark energy. But the numbers don't line up neatly. The gap between theory and reality is so massive, It's like predicting the height of Mount Everest and being off by the size of the observable universe. Some physicists think the answer lies in new physics. Maybe quantum fields behave differently on cosmic scales. Maybe gravity itself changes in subtle ways we don't yet understand. Others whisper about the multiverse, countless universes, each with different vacuum energies. Most too violent, too unstable to form stars, but one ours balanced on a knife's edge, a Goldilocks vacuum, just right for life. Still, the catastrophe remains. Every time we point to the stars, we're reminded the vacuum is lying to us. It looks calm, silent, empty, but beneath that calm, it hides the greatest discrepancy in physics. The void isn't nothing, it's everything, and it holds secrets that could rewrite reality itself. The vacuum catastrophe isn't just a problem, it's a clue, a flashing neon sign in the equations, screaming, "You don't understand the universe yet." And maybe that's the real mystery, that the deepest riddle isn't in galaxies or black holes, but in the nothingness between them. Albert Einstein. The name itself feels larger than life. He gave us relativity. He reshaped space and time. He bent the universe with equations. But even geniuses stumble. Even the brightest minds doubt themselves. In 1917, Einstein stared at his own math. His equations said the universe should be moving, stretching, expanding, or collapsing. But back then, everyone believed the cosmos was static, unchanging, a forever stage where stars simply shone. So, Einstein tweaked his masterpiece. He added a new term, a strange, invisible pressure baked into space itself. He called it the cosmological constant. It was a balancing act. Gravity pulled everything inward. The constant pushed everything outward. The two forces cancelled, holding the universe still, perfect, stable, safe, or so he thought. Then came 1929. Edwin Hubble pointed his telescope at the stars, and he found something shocking. Galaxies weren't sitting still. They were racing away from us. The universe was expanding. Suddenly, Einstein's constant looked unnecessary. A clumsy patch. A mistake. He called it his biggest blunder. A lesson in not forcing nature to fit our assumptions. But the story didn't end there. Fast forward to the late 1990s. Astronomers measured distant supernovae. They expected to find the expansion slowing down. Instead, they found it was speeding up. The universe wasn't just growing, it was accelerating. Something was pushing galaxies apart faster and faster. And the best way to explain it? The cosmological constant. Einstein's blunder had returned. Only now it looked like a stroke of foresight. Today, the cosmological constant is our simplest explanation for dark energy. That mysterious push is driving the acceleration of the cosmos. But there's a catch. The constant isn't a number we understand. It's a placeholder, a symbol for something deeper. Is it truly constant? Or does it change over time? Is it woven into the very fabric of reality? Or a shadow of hidden dimensions we can't yet see? We don't know. Not yet. Einstein thought he was patching an equation. Instead, he may have written the universe's most haunting riddle. The cosmological constant sits at the heart of modern cosmology. A ghost in the math. A whisper from the void. Blunder or prophecy? Perhaps both. Perhaps the line between mistake and discovery is thinner than we think. One thing is certain. Einstein's error turned out to be a key that unlocks the mystery of why the universe grows faster and faster with every heartbeat of cosmic time. And when we finally turn that key all the way, we may discover truths that Einstein himself never dared imagine. Imagine the universe as a game of balance. For every particle of matter, there should be a mirror twin, antimatter. Matter has a positive charge. Antimatter has the opposite. Bring them together and they annihilate. Gone. Pure energy. According to physics, the Big Bang should have made matter and antimatter in equal amounts. A perfect 50-50 split. Two teams locked in symmetry. But here's the kicker. If that symmetry were true, they should have wiped each other out instantly. No stars, no galaxies, no Earth, no us. The universe should be nothing but a cold bath of radiation, a lifeless flash of light. Yet here we are. Clearly, something tipped the scales. For some reason, matter got a slight advantage, just enough to survive the cosmic war. Maybe one extra particle in a billion. That tiny imbalance is the reason everything exists. But why? That's the mystery. Physicists call it baryon asymmetry. It's one of the biggest unsolved puzzles in science. What gave matter the edge over antimatter? We have some suspects. One theory says the laws of physics aren't perfectly symmetrical, that the universe favors matter subtly, secretly. Experiments with particles called kaons and B mesons hint at this bias. They show tiny differences in how matter and antimatter decay. A clue, a crack in the mirror. Another idea? The imbalance happened during the first split second of the Big Bang. When the universe inflated faster than light, quantum jitters may have skewed the odds. Matter won by a hair's breadth. Or maybe the answer hides in physics we haven't discovered yet. Hidden particles, unknown forces, rules of nature we've only glimpsed in the math. And then there's the wild card. What if antimatter isn't gone? What if it survived, but fled to another region of the cosmos? A mirror universe. Galaxies made entirely of antimatter, separated from ours by vast distances. If we ever touched boom, mutual annihilation. For now, these are questions without answers. But they strike at the core of existence itself. Why is there something rather than nothing? Why do stars shine, planets spin, and life emerge when the math says all of it should have been erased in an instant? The matter-antimatter problem isn't just a curiosity. It's the reason we're here to ask the question at all. Somewhere in the deepest laws of physics, a coin flipped, and it landed on the matter's side. That 1 in a billion chance is why you're reading this right now. The universe shouldn't exist, but it does, and that impossibility makes it one of the greatest mysteries we've ever faced. We picture space as a void, a blank nothing, an endless black canvas where galaxies float. But that's wrong, very wrong. Quantum physics says space is never truly empty. Even the most perfect vacuum stripped of all particles, all radiation is buzzing with activity. Invisible fields hum beneath the surface. Tiny fluctuations spark into being, then vanish. Particles appear out of nowhere, collide with their twins, and blink out again. They're called virtual particles. This chaos happens everywhere, all the time, inside every cubic inch of space. Even in the space between your eyes and this screen. To us, it looks empty, but at the quantum level, it's a storm. And here's the crazy part. These ghostly particles aren't just theoretical. They leave fingerprints. One famous example is the Casimir effect. Take two metal plates, put them extremely close together in a vacuum. The sea of virtual particles outside pushes harder than the smaller space between the plates. The result? The plates actually move pulled together by nothing. Proof that nothing is something. Another clue comes from black holes. Stephen Hawking predicted that quantum vacuum effects near the event horizon let particles escape. That's Hawking radiation, the reason black holes can slowly evaporate. So empty space doesn't just sit there. It shapes the universe. It fuels cosmic expansion. It whispers into the structure of reality itself. And yet, this is where mystery explodes. When physicists calculate how much energy the vacuum should contain, the answer is absurd. So absurd it's been called the worst prediction in science. Their equations suggest the vacuum's energy should be 10^² times larger than what we actually observe. That's a number so big it defies imagination. If the math were right, the universe would have torn itself apart instantly. Clearly, something's off. Either our math is broken, or we're missing a deeper law of nature. Some think the vacuum hides the key to dark energy, the force driving the universe's accelerated expansion. Maybe it's not just empty space pushing outward, but this restless vacuum energy bubbling beneath everything. Others think it points to physics beyond the standard model. New fields, new particles, or maybe an entire framework we can't even imagine yet. What's wild is that this mystery doesn't live out in some distant galaxy. It's here, right in front of you, right in your hand. Everywhere space exists, the vacuum is alive. So the next time you look up at the night sky and see the darkness between the stars, remember, it's not empty. It's the most crowded place you could imagine. The quantum vacuum may be the stage on which reality itself is written, and understanding it could be the key to unlocking why the universe behaves the way it does. We all live by the clock. Seconds, minutes, hours, days. Time feels simple. It ticks forward, steady and reliable. We measure it. We plan around it. We age because of it. But ask a physicist, what exactly is time? And suddenly, the ground vanishes beneath your feet. Time isn't like space. You can move left or right, up or down, but you can't walk backward in time. Not yet. Not ever, as far as we know. Einstein shattered our ordinary idea of time. He showed that time isn't absolute. It stretches, it bends, it slows down when you move fast. It warps near massive objects. That means your clock ticks differently from someone else's. Your time is not the same as theirs. There is no universal now. Strange, isn't it? But it gets even weirder. On the quantum scale, the equations of physics don't care about time's direction. A particle's dance can move forward or backward just the same. So, why, in our world, does time only march one way? We call this the arrow of time. It points from the past to the future, from order to disorder, from hot coffee to cold coffee. That's entropy, the second law of thermodynamics. But is entropy the whole story? Or just one layer of the puzzle? Some physicists think time is an illusion, that it isn't fundamental at all. It only emerges when the universe is big enough, complex enough, for change to appear. Others imagine time as a dimension, like space. The past, present, and future all exist at once. You're not moving through time. You're just experiencing one slice of the whole. If that's true, then your entire life from birth to death is already there, laid out in the fabric of space-time. The universe isn't unfolding. It's already written. But if that's the case, why do we feel time flowing? Why do we feel now? No one knows. And that might be the greatest mystery of all. Because without time, nothing makes sense. No cause, no effect, no change, no becoming. Maybe time is the heartbeat of the universe. Maybe it's the most human invention of all. Or maybe, just maybe, it's the key to unlocking everything we don't yet understand. So when you glance at a clock, remember, you're staring at the most slippery concept in existence. The invisible river that carries you forward, but a river whose source and whose end remain hidden in the dark. You wake up, the alarm rings, the day begins. You move from yesterday to today to tomorrow, always forward, never back. That is the arrow of time, the silent rule of the universe, the law we all obey. But why? Why can't we rewind? Why does milk only spill outward, never leap back into the glass? Physics makes it stranger. At the microscopic level, the equations of motion don't care about direction. They work the same backward as forward. A single particle could move either way. Yet our world doesn't. The past feels fixed, the future feels open, and the arrow points one way only forward. The key word here is entropy, a measure of disorder, of randomness, of chaos. In the beginning, the universe was low simple, uniform, hot and dense. Over time, things spread out, structures broke down, order unraveled, entropy increased, and keeps increasing. That rise in entropy is what gives time its arrow. It's why eggs crack but don't uncrack, why fires burn but don't unburn. As you grow older, not younger, it's the march from order to disorder, from neat beginnings to messy endings. But there's a deeper puzzle. Why did the universe start in such a low entropy state? Why did the cosmic clock begin wound so tightly? No one knows. Some think it's built into the laws of physics. Others believe it was a cosmic accident. Or maybe entropy itself is just part of a bigger pattern we don't yet see. Here's another twist. Black holes. When matter falls in, entropy spikes. Black holes may hold the highest entropy in the universe, the ultimate storage of disorder, perhaps even the vault of time's arrow itself. And then there's the far future. If entropy always rises, what happens when it can't rise anymore? That's heat death. A universe where everything is balanced. No heat flows. No processes run. No arrow of time. Imagine it. A cosmos with no before and after. Only stillness. Only silence. So maybe the arrow of time isn't eternal. Maybe it's just a phase, a temporary flow through a deeper, timeless ocean. And here we are, caught in the current, living one moment after another, never able to look back. The arrow of time defines our existence, but its origin remains one of the greatest mysteries in all of physics. So the next time you watch a sunset, remember that fading light is more than beauty. It's entropy at work. The arrow of time is pulling everything forward, taking us further into the unknown. The Big Bang, the ultimate starting line, the birth of space, the birth of time. But hold on, if time began there, what does before even mean? It's like asking, what's north of the North Pole? The very question bends in on itself. And yet, curiosity pushes us to ask, what happened before the Big Bang? One idea, nothing at all. No before, no ticking clock. Time itself switched on with the bang, but physicists don't stop there. Some theories imagine a cyclic universe, where big bangs and big crunches repeat endlessly. A cosmic heartbeat. Bang, expand, collapse, repeat. If that's true, our universe might be just the latest cycle. Another idea, the multiverse. Picture a vast cosmic sea where bubbles of universes pop into existence. Our Big Bang? Just one bubble in an infinite froth. Before us, others. After us, more. The beginning of time in this bubble, but not in the larger multiverse. Then there's quantum cosmology. At the smallest scales, reality fuzzes. Quantum rules replace classical logic. Maybe the Big Bang wasn't a singularity at all, but a quantum bounce, a rebound from a collapsing universe that came before. And here's the strangest thought. Maybe the question before makes no sense, because time itself is emergent, like waves on the ocean, like heat in a crowd, not fundamental, but a property of deeper laws. If so, before might be a human illusion. The universe doesn't care about our words. But one thing's clear, the Big Bang isn't the final answer. It's the doorframe. Beyond it lies mystery, possibly the greatest mystery of all. Think about it. Every galaxy, every star, every life, everything you know, sprang from that one moment, that one boundary, and we're left with the question, what lit the fuse? The truth? We don't know, and maybe we never will, but the pursuit itself drives science forward. Every theory, every telescope, every mind daring to wonder pushes us closer. So next time you look up at the night sky, remember, the story of the cosmos isn't finished, and the biggest chapter may still lie before the beginning. Because to ask, what happened before the Big Bang? It isn't just science, it's philosophy, it's imagination, it's humanity refusing to stop asking why. And that is where wonder lives. If you love diving into these cosmic mysteries, make sure to subscribe, because the next big question is waiting, and you don't want to miss it. We take time for granted. Seconds ticking, clocks moving, days turning into years. But what if time itself runs out? Not just for you, not just for Earth, but for the entire universe. Let's start with entropy, the great driver of time's arrow. Entropy means disorder spreads. Things fall apart. Energy evens out. The universe heads toward heat death. When maximum entropy arrives, nothing changes. No processes run. No clocks tick. That's not just the end of stars. That's the end of time itself. But that's only one version of the story. Some theories say the universe might not fade. Instead, it could tear apart. Dark energy keeps accelerating the expansion. Galaxies rush away. Then stars, then planets, then molecules, then atoms, until even the fabric of space rips. If that big rip happens, time doesn't fade, it shatters. The future itself is cut short. Other physicists suggest a different twist. What if time is an illusion, a construct of how we perceive change? If so, when change itself stops, so does time. No ticking, no flow, just stillness. And there's the quantum view. At the tiniest scales, time may not be fundamental at all. It might emerge like temperature emerges from particles. In that case, the end of time isn't destruction, it's a phase change, a shift to some deeper, timeless reality. Think about it. We fear death because it's the end of our personal time. But imagine the death of all time. No future, no past, just a frozen cosmos. Or worse, a universe that stretches time so thin, so distorted, that no event ever follows another. A universe where next has no meaning. Is that silence? Or is it freedom? The end of time raises questions bigger than physics. What does it mean to exist when there's no time to measure existence? Does reality itself vanish? Or is there something beyond time that we can't even imagine? The universe began with the birth of time. It may end with time's final breath. And in between, we get this sliver, this precious window to ask questions, to live, to wonder. Maybe time is a river. Maybe time is an illusion. But one day, that river may dry up. And when it does, the story of the universe closes. Not with a bang, not with a whimper, but with no more time left to tell it. Look up at the sky. You see stars scattered across space. But what shape is that space? Flat? Curved? Or something we haven't even imagined? This isn't a trivial question. The shape of the universe decides its fate. Whether it keeps expanding forever, whether it collapses back in on itself, or whether it loops in strange, endless ways. So, let's break it down. If the universe is flat, parallel lines never meet. Geometry works like it does on your school desk. The angles of a triangle add up to 180. In a flat cosmos, expansion continues forever. Galaxies keep drifting apart. It's endless, infinite, unbounded. If the universe is positively curved, think of a sphere. Parallel lines eventually cross. Triangles add up to more than 180. In a curved cosmos like this, the universe might one day stop expanding. Gravity could pull everything back, ending in a fiery big crunch. If the universe is negatively curved, picture a saddle. Lines spread apart faster and faster. Triangles add up to less than 180. This universe expands forever too, but with even more dramatic separation. Galaxies vanish into darkness faster than in a flat model. So, which is it? Cosmic microwave background radiation holds the clues, that faint afterglow of the Big Bang. By measuring tiny ripples in that light, astronomers can map cosmic geometry. And the shocking result? The universe looks flat, almost perfectly flat. But here's the twist. Flat doesn't mean boring. It could be infinite. Or it could be finite, but unbounded, like a video game map that loops back on itself. Travel far enough in one direction, and you might return to where you started. Then there's inflation theory, a rapid ballooning of space in the early universe. It predicts flatness, but also opens the door to wild possibilities. Pocket universes, multiverse structures, shapes stranger than we can picture. Here's the mind bender. The universe might not have a shape in the way we think. Shape is a human concept, born from 3D objects, but space-time may curve in dimensions we can't perceive. Curvature beyond our senses. A shape stranger than sphere, saddle, or flat plane. So when we ask, what is the shape of the universe? We're really asking, what is reality itself curved upon? Flat, curved, or alien to our minds? The shape of the universe isn't just geometry. It's destiny. If it's flat, expansion never stops. If curved, collapse might return us to the beginning. If a stranger, we're left standing at the edge of imagination. And maybe that's the point. The cosmos keeps its deepest truth just out of reach. We measure, we model, we wonder, but in the end, the shape of the universe is also the shape of our own curiosity. Boundless. The universe is restless. It doesn't sit still. It stretches. It grows. It expands. And here's the wild part. It's been doing this since the very beginning. When the Big Bang erupted 13.8 billion years ago, space itself was born, and from that instant, it hasn't stopped stretching. At first, scientists thought gravity would slow it down. After all, gravity pulls everything together. Surely the expansion would weaken, maybe even reverse. But no, the opposite happened. Not only is the universe expanding, it's accelerating. So, why won't it stop? Because expansion isn't things flying apart in space. It's space itself stretching. Galaxies aren't moving through space like cars on a road. The road itself is lengthening. The distance between galaxies increases, even if they're just sitting there. Edwin Hubble first spotted this in the 1920s. He saw galaxies rushing away from us. The farther they were, the faster they receded. Like raisins in rising bread dough, every part of the dough moves apart. As the whole thing swells, that's the cosmic expansion. Simple, but unsettling, because if it keeps going, everything we know drifts away. Stars fade into darkness. Galaxies vanish beyond view. The night sky grows emptier and emptier. And here's the kicker. We don't know exactly what's driving it. Dark energy is the leading suspect. A mysterious pressure hidden in empty space. Something is pushing galaxies apart. Something stronger than gravity itself, and it's everywhere. Not clustered like matter. Not bound like stars. Spread evenly through the fabric of space. As space expands, more dark energy emerges, fueling even faster expansion. A cosmic feedback loop. So the universe won't stop. It can't stop. Expansion is built into its very nature. Will it expand forever? Most likely. But there are other theories. Some say expansion could end in a big rip. Galaxies torn apart. Stars shredded. Even atoms are ripped into pieces. Others imagine a big crunch. Expansion slowing, reversing, collapsing everything back into one. But evidence points elsewhere. All signs say expansion keeps accelerating. No brakes. No pause button. Here's the haunting thought. Every second, more of the universe slips beyond our reach. Distant galaxies move away faster than light can carry their signals. They become invisible, lost forever. Our cosmic horizon shrinks, even as the universe grows. So, why won't it stop? Because the universe isn't just expanding in space, it is space, and space is still unfolding. Endless, relentless, mysterious. The universe is still growing, and one day, it may grow beyond everything we can ever know. Look up at the night sky. Every tiny point of light isn't just a star. It might be an entire galaxy, a city of stars, billions of suns bound together. But here's the puzzle. How did these star cities come to be? We know the story starts after the Big Bang. In the beginning, the universe was a glowing fog, hot, dense, chaotic, no stars, no galaxies, just energy, particles, and radiation. Then, things cooled. Gravity got to work. Tiny clumps of matter formed. Those clumps grew, gas collected, stars ignited, and those stars are grouped into galaxies. But the mystery is deeper. Why did galaxies take such different shapes? Some became beautiful spirals, like our Milky Way. Others grew into giant ellipticals, round, swollen spheres of stars. And some are strange, irregular smudges. It seems galaxies don't just form. They evolve. They collide. They merge. They tear each other apart, only to rebuild into something new. Our own Milky Way is proof. It wasn't born perfect. It grew by swallowing smaller galaxies. Even today, it's still at it. On the edges of our galaxy, you can find the remnants of old star systems that the Milky Way consumed, and in about 5 billion years, will collide with Andromeda. 2 galaxies, 2 star cities, merging into one giant metropolis of stars. But here's the hidden twist. Galaxies couldn't form without something invisible. Dark matter. It's the unseen framework. The skeleton holding galaxies together. Without it, stars would fly apart. Gravity alone isn't enough. So, these vast star cities exist because of a mysterious substance we still don't understand, and it gets stranger. At the center of almost every galaxy lurks a supermassive black hole, millions, even billions of times heavier than the Sun. Why are they there? Did galaxies form around black holes? Or did black holes grow because galaxies formed? We don't know. Think about it. Every galaxy, no matter how different, seems to share this feature. It's as if black holes and galaxies are partners in creation. So, what are galaxies really? Not just star cities. They are engines of evolution, forges of heavy elements, the birthplaces of stars, planets, and maybe even life itself. Without galaxies, there would be no Earth, no Sun, no us. And yet, the full story of how they formed and why they look the way they do, it's still a riddle, a cosmic mystery, written in starlight. The next time you see the Milky Way stretching across the sky, remember, it's not just a band of stars. It's our city in the universe, one among billions, each with its own story, its own mystery, still waiting to be solved. At the core of almost every galaxy lurks a monster, a beast so powerful it bends space and time itself. A supermassive black hole, millions, sometimes billions of times heavier than our Sun, yet packed into a region smaller than our solar system. An object so extreme that not even light can escape. The Milky Way has one. We call it Sagittarius A. It's about 4 million solar masses, sitting quietly at the heart of our galaxy. But don't let that calmness fool you. It's a cosmic predator. So, here's the mystery. Why do black holes exist at the center of galaxies? Did they form first, acting as seeds, which galaxies grew? Or did galaxies form first, and then feed their central giants? Astronomers don't have the full answer, but one thing is clear. Supermassive black holes are essential to the life cycle of galaxies. When gas and dust fall in, they don't always disappear quietly. Sometimes, the black hole gets greedy. It devours matter so quickly. That energy explodes outward. Jets of radiation shoot across space, brighter than the light of 1 trillion stars. We call these monsters quasars. Quasars are lighthouses of the early universe. They tell us black holes have been shaping galaxies since the beginning. Without them, galaxies might not look the way they do today. And yet, black holes aren't just destroyers, they're also creators. By blasting energy, they can regulate star formation. They decide whether a galaxy is calm or blazing with newborn stars. In a way, black holes are cosmic architects. But let's get real for a second. What happens if you fall in? First, you'd be stretched, spaghettified, your atoms pulled apart. As you spiral into the abyss, past the event horizon, the point of no return. From the outside, you'd simply vanish. Your information is lost to the universe. Or maybe not. Physicists still debate what happens to information inside a black hole. It's one of the greatest puzzles in science. And remember, the one in our galaxy is quiet for now. But galaxies merge, and when that happens, their black holes merge too. The result? An even bigger monster, one that shakes space itself, sending ripples of gravity across the cosmos. We've already detected these ripples, gravitational waves, proof that black holes, it isn't just a theory, they're real, and they're violent. So next time you picture a galaxy, don't just think of its stars. Remember the dark heart at its center, a supermassive black hole, silent, patient, waiting, a reminder that the universe is not only beautiful, but terrifying. And the deeper we look, the more we realize these monsters may hold the key to understand the evolution of everything. Imagine looking deep into the night sky, farther than any star you've ever seen, and spotting a light so bright it outshines entire galaxies. That's a quasar. At first, astronomers thought they were stars, quasi-stellar objects, they called them. But soon, the truth emerged. These weren't stars, they were the hearts of galaxies, powered by supermassive black holes feeding like beasts. Here's how it works. Gas and dust spiral inward. They heat up as they fall. Friction turns them into a cosmic furnace. Temperatures rise to millions of degrees. Radiation blasts out. X-rays, gamma rays, visible light, the whole spectrum. A quasar is the brightest beacon in the universe. Some quasars are so far away that their light has taken billions of years to reach us. When we see them, we're looking back in time to the early universe. They tell us black holes were active even then, that galaxies were already alive with energy. But quasars have cousins, even more extreme, blazars. A blazar is what happens when a quasar's jet points straight at us. Imagine a fire hose of energy shooting directly into your eyes from billions of light years away. That's a blazar. It flickers, it flares. Sometimes it changes brightness in just hours. That's how powerful it is. And here's the mystery. How can a black hole, an object that swallows everything, also shine so brightly? The paradox is fascinating. Black holes trap light, yet the process of feeding them creates the brightest lights in the cosmos. Quasars and blazars are more than just pretty shows. They're tools. Astronomers use them like flashlights to probe the distant universe. Their light passes through gas and dust along the way, and by studying that light, we can learn about everything it touches. It's like reading the fingerprints of the cosmos. Without quasars, we might never know what the early universe looked like. Without blazars, we might not understand how black holes launch jets across intergalactic space. But there's still so much we don't know. How exactly do black holes launch jets? Why are some galaxies quiet, while others blaze with quasar fire? And will every galaxy go through a quasar phase? Or just a few? What we do know is this. Quasars and blazars remind us that the universe is a place of extremes, blinding light born from infinite darkness. Destruction creates creation. Black holes are becoming lighthouses. So when you look up at the night sky, remember this. Some of those faint dots of light, they aren't stars at all. They're ancient explosions of energy. billions of years old, guiding us like beacons across the cosmic ocean. Quasars and blazars, proof that the universe loves drama, and it never runs out of mysteries. Picture a line in space, invisible, uncrossable, the point of no return. That's the event horizon of a black hole. Cross it, and there's no way back. Not for you, not for light, not for anything. It's the ultimate one-way ticket, a cosmic trap, the edge of reality itself. But here's the mystery. What happens to information that falls inside? Physics says information can't be destroyed. Every particle, every wave, every detail of reality leaves behind a trace. It has to be conserved. But black holes seem to disagree. Drop a star into one, and all you see from the outside is the black hole getting heavier. The details of the star vanish. Its composition, its shape, its entire history, gone. So, does the event horizon erase information, or hide it in ways we can't yet see? Stephen Hawking wrestled with this puzzle. In the 1970s, he showed that black holes aren't eternal. They radiate, slowly, fading over time. We call it Hawking radiation. But there's a catch. That radiation looks random. No signs of the star that once fell in. If the black hole eventually evaporates, and the information is gone, then physics breaks. The laws of the universe contradict themselves. This is the information paradox, and it all starts at the event horizon. Some theories suggest the information isn't lost, it's scrambled, encoded in subtle ways. On the surface of the horizon, like a cosmic hologram, others imagine that space-time itself bends in strange ways. Those wormholes, quantum foam, or even multiverse leaks preserve the missing data. And then there's the bold idea that the universe we live in, it is fundamentally holographic. That every three-dimensional object, it is actually encoded on a distant two-dimensional surface. If true, then the event horizon isn't a wall. It's a storage system, the greatest cosmic archive. But until we truly understand, the question remains, is the event horizon a shredder or a librarian? What happens to identity, to history, to the building blocks of existence? When they cross that edge, we may never witness it directly, because no signal escapes to tell us the truth, but still, we push forward through equations, through telescopes, through imagination, the event horizon, the most mysterious border in the universe, a place where science trembles, and reality itself may be rewritten. Black holes, the darkest, most inescapable objects in the cosmos. Or are they? For decades, scientists believed nothing could escape a black hole. No matter, not energy, not even light. Then Stephen Hawking flipped the script. In the 1970s, Hawking made a shocking prediction. Black holes aren't completely black. They glow, they leak, they can even vanish. This radiation, now called Hawking radiation, is one of the greatest paradoxes in physics. Here's the wild part. It all comes from empty space. Quantum physics tells us that empty space isn't truly empty. It seethes with energy. Virtual particles pop in and out of existence. One particle, one antiparticle. A pair, born together, doomed to annihilate each other in an instant. But near the event horizon of a black hole, this cosmic dance takes a strange turn. Imagine a particle-antiparticle pair forming right at the edge. One falls into the black hole, the other escapes into space. To an outside observer, it looks like the black hole is radiating, losing energy, shrinking. Over trillions upon trillions of years, this process could cause a black hole to evaporate completely. The most unstoppable objects in the universe. It could simply fade into nothing. Sounds neat, right? Not so fast. Here's the paradox. If black holes evaporate, what happens to the information about everything that fell inside? Drop in a star, a planet, or even your Netflix password. Eventually, the black hole disappears. But where did the information go? Quantum theory says, information can never be destroyed. It must be preserved. Somehow, somewhere. But Hawking radiation looks completely random. No trace of what went in. No code. No history. Nothing. That's the paradox. If black holes really evaporate, we're forced to choose. Either accept that information can vanish, breaking the foundations of physics, or accept that our theories are incomplete, and reality works in ways we don't yet understand. Physicists have fought over this for decades. Some argue the information is encoded in the radiation itself, just extremely scrambled, like burning a book into smoke and ash, but still recoverable if you have infinite patience. Others suggest black holes store the information on their surfaces, as if the event horizon were a giant cosmic hard drive, a hologram of everything that ever fell in. And then there are wilder ideas. Wormholes, alternate universes. Quantum entanglement preserves the data in places we can't reach. But the truth? We don't know. Not yet. Hawking radiation remains one of the strangest predictions ever made. It tells us black holes might die, that even the mightiest giants of the cosmos are temporary. And it leaves us with a haunting question. When the last black hole evaporates, will the universe still remember what once was? Or will all history be lost to the void? When you hear galaxies collide, it sounds like the ultimate cosmic disaster. A train wreck scaled up to 1 trillion stars. But here's the twist. Galactic collisions aren't just chaos, they're engines of creation, the universe's way of reshaping itself. Let's break it down. Galaxies are vast, hundreds of thousands of light years across. Yet, most of that space is, well, space. Stars are so far apart that when two galaxies slam together, individual stars almost never crash head-on. Instead, what really collides? The gas, the dust, the invisible dark matter halos surrounding them. As galaxies approach, their mutual gravity stretches and twists them. Spiral arms warp. Tidal tails fling stars like sparks from a fire. Vast clouds of gas compress. And that's where the magic happens. Starbirth. Massive bursts of star formation. So intense they're called starbursts. A single galactic merger can light up millions of new suns. The destruction feeds creation. Want an example? Look at the antennae galaxies. Two spirals in the middle of a slow-motion smash. Their elegant arms stretched into long antenna-like tails. At their heart, thousands of newborn star clusters. Each one could grow into a mini-galaxy of its own, or the Whirlpool galaxy interacting with its smaller companion. Gas streams between them, igniting fresh waves of star formation. And it's not just stars. Collisions can awaken the sleeping giants at galactic centers. Supermassive black holes, usually quiet, suddenly get fed with torrents of gas. They flare into active galaxies. Some blast out quasars. Lighthouses are visible across the universe. Now, let's bring it home. Our own Milky Way isn't immune. We're on a collision course with Andromeda. A galactic dance is already set in motion. In about 4 to 5 billion years, the two spirals will begin their slow embrace. What will it look like? First, the skies will fill with strange new patterns. Andromeda will loom larger and larger. Streams of stars will arc across the heavens. Then, as the galaxies intertwine, starbursts will light up the night. Finally, the two will merge into a single giant. A massive elliptical galaxy astronomers have already nicknamed Milkomeda. Will Earth survive? Probably. Remember, stars rarely crash directly, but our position in the galaxy could shift. We might be flung farther from the center, or pushed into new stellar neighborhoods. Either way, the sky our descendants see will be utterly transformed. Here's the bigger picture. Collisions are not rare accidents. They are part of cosmic evolution. Galaxies grow by merging, just like rivers join into greater streams. In fact, without collisions, galaxies like the Milky Way might not even exist. Destruction and creation, chaos and order, this is the rhythm of the universe. When we look at colliding galaxies through telescopes, we're not just watching explosions, we're watching the life cycle of the cosmos itself. Galaxies die as individuals, but they are reborn as something greater. The wreckage becomes the foundation of new stars, new planets, and maybe even new life. So the next time you see an image of a galactic smash-up, don't think of it as a disaster. Think of it as the universe sculpting itself, writing new stories in the stars. Because in the cosmos, even destruction is just another form of creation. This is the big one, the question that keeps us awake, that haunts every late-night stargazer. Are we alone in the universe? Think about it. There are more stars in the cosmos than grains of sand on Earth. Around those stars, countless planets. Many are in habitable zones, not too hot, not too cold, just right for liquid water. With numbers that staggering, how could Earth be the only place with life? And yet, silence. Let's start with what we know. Life on Earth appeared quickly, barely a few 100 million years after the planet cooled. That suggests life, under the right conditions, might not be rare. It might be the rule, not the exception. Microbes could be common across the galaxy, hidden under icy crusts, floating in alien atmospheres, clinging to strange chemistries we've never imagined. But intelligent life? That's another story. Civilizations, technology, signals across the stars. That's the real mystery. We've been listening for decades, scanning the skies with radio telescopes, waiting for a cosmic hello. What week in different to different? So far, nothing. No signals. No alien transmissions. Only static. This is called the Fermi paradox. With so many stars, so many planets. Where is everybody? Some say civilizations rise, but burn out quickly. Wars, exhausted resources, extinctions. Maybe intelligence is fragile, a brief spark that fizzles before it spreads. Others argue we might be too early. The universe is still young. Civilizations may not have had time to bloom everywhere. We could be one of the first, or maybe they're out there, but staying quiet. A galactic prime directive. Don't interfere. Don't reveal. Observe us silently until we're ready. There's another possibility. We might be looking wrong. Maybe aliens don't use radio at all. Maybe they communicate with technologies we can't even imagine. Quantum entanglement, neutrino beams, dimensions we don't yet understand. Meanwhile, right here in our solar system, we have intriguing candidates. Mars once covered in rivers and lakes. Europa, Jupiter's icy moon with a hidden ocean. Enceladus, Saturn's moon shooting geysers of water into space. These worlds could host life today. Not intelligent life, but microbes, little alien cells, rewriting biology as we know it. If we found even a single microbe elsewhere, it would change everything. Because if life can start twice, even in one solar system, it means the universe is teeming with it. And if the universe is teeming with life, then somewhere out there must be other minds. Imagine it. Civilizations are billions of years older than ours. Technology that makes us look like children with sticks. Would they be explorers, builders, peaceful philosophers, or conquerors moving from star to star? We don't know. And that's the greatest mystery of all. Here's the paradox. The universe feels too vast for us to be alone, but so far, the evidence says we are. So we keep searching. We send probes. We listen to the stars. We scan the skies for signs of distant engineering, because the answer, yes or no, changes everything. If we are alone, then life is unbelievably rare, precious, fragile, and our responsibility is enormous. If we are not alone, then we are part of something greater. a cosmic community waiting to be discovered. Either way, the mystery of alien life defines our place in the universe. And until we solve it, the night sky will always whisper the same question. Are we truly alone? It's one of the simplest questions, and one of the most unsettling. Where is everybody? With billions of galaxies, trillions of stars, and untold numbers of planets, you'd expect the universe to be buzzing with life, civilizations, signals, signs of technology. Yet silence. This puzzle is called the Fermi paradox, named after physicist Enrico Fermi. One day, during lunch in 1950, he asked the question, if aliens exist, where are they? The logic is brutal. Even at modest speeds, a civilization could colonize the galaxy in just a few million years. That's a blink on cosmic timescales. So, if others exist, the galaxy should already be full of evidence, but we don't see it. Not a whisper, not a beacon, not a trace. So what's going on? There are many possible answers. None of them is comforting. One idea: life is rare. Yes, planets are common. Yes, stars are everywhere. But maybe the leap from chemistry to biology is incredibly unlikely. Perhaps Earth is a cosmic lottery winner. Another idea: life is common, but intelligence is rare. Simple organisms may fill the universe. Bacteria, microbes, tiny alien cells. But the leap to complex thinking creatures, that may almost never happen. A darker possibility: intelligence destroys itself. Civilizations rise, they invent technology, but eventually they burn out. War, climate collapse, exhaustion of resources. The galaxy might be littered with the ruins of species that didn't last long enough to spread. Or maybe we're simply early. The universe is still young. Stars will keep forming for trillions of years. We might just be among the first pioneers in a cosmos that hasn't yet fully awakened. There's also the Great Filter theory, the idea that somewhere between the birth of life and the rise of advanced civilizations, there's a deadly barrier, a step so hard, so unlikely, almost nobody passes it. The question is, have we already passed it, or is it still waiting for us ahead? Then there's the zoo hypothesis, the notion that aliens are out there, watching us, but staying quiet, like humans, observing animals in a reserve. Hands off, no interference. Let the young species grow on its own. Some take it even further. Maybe aliens are here. Maybe they've always been here, but hidden, invisible to our senses, operating on scales or technologies we can't even perceive. And maybe we're just looking the wrong way. We expect radio signals, but advanced civilizations might use methods beyond our imagination. Quantum communication, wormholes, signals written into the very fabric of space. The silence could be an illusion. The universe might be alive with conversation. We just don't have the ears to hear it. The Fermi paradox is not just a question. It's a mirror. It forces us to confront our own future. If civilizations burn out, will we? If life is rare, are we its only voice? If others are hiding, what does that say about us? Where is everybody? The truth may be terrifying, or inspiring, or something we can't yet imagine. But one thing is clear: until we answer it, every star we see in the night sky carries the same haunting whisper. Are we alone? Or is the silence just the beginning of a much bigger story? If you're looking for life, you can't just point at any planet and say, "Yep, that'll do." Life is picky. It needs a world that's not too hot, not too cold, but just right. Astronomers call this the habitable zone, but the nickname is even better: the Goldilocks zone, straight out of the fairy tale. It's the narrow band around a star, where liquid water can exist on a planet's surface, and liquid water is the magic ingredient. On Earth, every form of life we know depends on it. So, when scientists scan the skies, water is the first thing they hunt for. Think about our own solar system. Earth sits perfectly in the Goldilocks zone. Mars is close, but it's on the edge. Too cold, too thin an atmosphere to hold liquid water for long. Venus is the opposite. Same size as Earth, but trapped in a runaway greenhouse effect. Oceans boiled away. The surface is hot enough to melt lead, just a little too close to the sun. Shift Earth a few million miles in either direction, and life as we know it might never have happened. That's how razor thin the balance is. Now, scale that idea up. Our galaxy has about 200 billion stars. Many of those stars have planets, and with new telescopes, we're finding Earth-sized planets, sitting right in that just right zone. Some stars orbit smaller and cooler than the Sun. Some orbit stars bigger and hotter. But in each case, if the orbit is right, liquid water is possible. And where there's water, there's a chance for life. But here's the twist. The Goldilocks zone isn't just about distance. A planet also needs the right atmosphere, the right chemistry, the right stability. Take Mars again. It technically sits in the Sun's habitable zone, but without a strong magnetic field, the solar wind stripped away its atmosphere. No atmosphere, no pressure. No pressure, no stable liquid water. So the zone alone isn't enough. And then there's the super-Earths, planets larger than ours. Some are in their star's Goldilocks zone. Could they have thick atmospheres, deep oceans, even continents? They may be even more just right than Earth. Astronomers are obsessed with one goal: finding an Earth twin, a planet with the same size, the same rocky makeup, orbiting in the habitable zone of a calm, steady star. And the hunt is heating up. The Kepler Space Telescope revealed thousands of candidates. The James Webb Space Telescope is now analyzing their atmospheres, looking for fingerprints of life, oxygen, methane, water vapor, clues that something is breathing. Here's the kicker. Estimates suggest that in the Milky Way alone, there could be billions of planets in the Goldilocks zone. Billions. That means, statistically, life should not be a rare miracle. It should be common. The real mystery isn't whether other just right planets exist. We know they do. The mystery is whether life actually takes hold, and whether it evolves far enough to look back up at the stars and wonder the same things we do. So the Goldilocks zone is more than just a cosmic sweet spot. It's a reminder of how fragile life is, how perfectly balanced the Earth turned out to be, and how many other chances the universe may have rolled the dice on. Maybe we're not unique. Maybe the galaxy is sprinkled with other blue planets, other oceans, other minds asking the same question. Are we alone? Or is life written into the very fabric of the cosmos, just waiting for the right planet, in the right place, at the right time? When people imagine aliens, the picture is almost always the same. Small, green, big heads, huge black eyes, Hollywood's favorite design. But here's the truth. If extraterrestrials exist, they probably look nothing like that. Why? Because evolution doesn't follow a script. It adapts to its environment. And out there, environments are wild. Let's play the thought experiment. On a planet with higher gravity than Earth, creatures might need short, stocky bodies, strong muscles, thick legs, built to push against a heavier world. On a planet with low gravity, life could be tall, thin, and spindly, creatures drifting lightly, maybe even floating. Now, imagine a world drenched in radiation. Life there might evolve protective shells, metallic-like skin, or the ability to repair DNA instantly. What about a planet covered in oceans? Aliens there might never crawl onto land. They could be squid-like, or jelly-like, using sonar instead of eyes. And then there's the extreme, planets with no sunlight, orbiting dead stars. Life could feed off chemical reactions, glowing, eyeless, thriving in eternal darkness. The diversity is endless. Here's the real twist. Aliens might not even have bodies as we think of them. They could be swarms of microbe-like organisms, or hive minds, or beings made of plasma, energy, or something we can't even imagine. Think about Earth's own life. We've got creatures that breathe sulfur, insects that see ultraviolet, bacteria that survive inside volcanoes. If that's possible here, what's possible out there? But let's turn it around. Why do people picture aliens as humanoid? 2 arms, 2 legs, a head. It might not just be vanity. There could be logic. If you want to build tools, you need grasping limbs. If you want intelligence, you need a brain safely packed in a head. Eyes near the top for awareness. So maybe, just maybe, evolution tends to favor something vaguely humanoid. The truth? We can't know until we actually meet them. And that's the mystery. Would they be terrifying giants? Would they be microbes so small we wouldn't notice? Would they be beautiful or completely incomprehensible? And here's the bigger question. If they are intelligent, how would we react? Would we even recognize them as alive? What if they communicate in ways we can't detect? Magnetic fields, chemical scents, or quantum signals? Right now, it's pure speculation. But every new exoplanet we discover, every new biosignature we hunt, brings us closer to the day when speculation might turn into reality. And when that day comes, the biggest shock might not be what they look like, but how much they remind us of ourselves. Because the real alien mystery isn't about shape or size. It's about connection. What happens when 2 intelligent species meet for the very first time? One thing's for sure, the universe is too creative to have made us the only show in town. So keep watching the skies. Because the day we see alien faces, they may not look like little green men at all, but they'll change our view of life forever. If you want to keep exploring mysteries like this, from alien life to the edge of the universe, make sure to subscribe. The biggest discoveries are still ahead, and you don't want to miss them. What if I told you that everything you see, everything you hear, everything you feel might not be real at all? Not the stars, not the galaxies, not even you. Sounds impossible, right? But that's the simulation hypothesis. The idea that our entire universe is just code, a program running on some higher being's computer. Crazy? Maybe. But here's the twist. Some of the smartest minds on Earth take this idea very seriously. Think about it. In just a few decades, humans built video games so real, you can get lost in them. VR so immersive, you forget the outside world. Now, imagine a civilization 1,000,000 years ahead of us. Their computers wouldn't just simulate a city or a planet, they could simulate a whole universe. Every star, every galaxy, every conscious being, all inside a vast program. Here's the kicker. If it's possible to simulate reality, then statistically, there are probably more simulated universes than real ones. So, the odds that we're in the one real universe start to look very, very small. But how would we know? That's the real mystery. Some scientists suggest clues. Maybe the universe is made of pixels, not visual ones, but tiny, indivisible units of space and time, like resolution in a video game. Zoom in far enough, and maybe reality itself looks blocky. Others wonder about physics, patches. Why do the laws of nature feel so perfectly tuned for life? Maybe it's because the code was written that way. And here's the wildest part. Quantum mechanics, particles that exist in many states until someone observes them. Is that reality, or is it code loading? Only when we look. If the simulation idea is true, then what about us? Are we just programs? Or do we have free will? Are our choices real? Or are they just lines of code, running exactly as written? Some people find this terrifying, others find it liberating. Because if reality is a simulation, then death may not be the end. We might just be logged off, saved, or rebooted in another form. But here's the paradox. If we're in a simulation, then who built it? Note, and if they built it, are they in a simulation too? Layer upon layer, like Russian dolls of reality. Maybe the biggest mystery is not whether the universe is real, but whether the concept of real even matters anymore. Because for us, this is real. The stars, the galaxies, the questions we ask, even if it's all running in some cosmic code, it feels real enough to us. And maybe that's the point. So, the next time you look at the night sky, ask yourself, is that a billion stars out there? Or is it just the background rendering? Either way, the mystery remains. And sometimes, it's the mystery itself that makes life worth living. Earth feels ordinary. We wake up, we see the sky. We live on a blue planet circling a star. It doesn't seem that special, but what if I told you it might be one of the rarest things in the entire universe? That's the rare Earth puzzle. The idea that intelligent life, maybe even life at all, is far, far rarer than we think. Here's why. Step 1. The right star. Not too big, not too small. Big stars burn out fast. Small stars flare like firecrackers. Our sun, middle-aged, stable, perfect. Step 2. The right distance. The Goldilocks zone. The Goldilocks zone. Not too hot, not too cold. Water can flow, oceans can form, life can begin. But wait, that's just the start. You also need the right kind of planet. Solid rock, not a gas giant, not a frozen ball of ice. It needs an atmosphere, but not too thick, or it smothers life. Not too thin, or water boils away. Then there's the magnetic field, a shield protecting us from deadly solar radiation. That comes from Earth's molten core, churning iron like a cosmic dynamo. And don't forget the moon. Our oversized moon stabilizes Earth's tilt. No moon, wild climate swings. Seasons are out of control. Maybe no stable environment for life at all. Then, plate tectonics. Yeah, moving continents. Sounds destructive, but it recycles carbon. It keeps Earth's climate in balance for billions of years. Without it, Earth could have turned into Venus, a hellish greenhouse. Every single one of these factors had to line up perfectly, and they did. Now think bigger. The galaxy is dangerous. Supernovas, gamma-ray bursts, black holes swallowing stars. Earth happens to sit in a calm neighborhood, not too close to the galactic core, not too far in the suburbs. We orbit in the galactic habitable zone. Add it all up, and the odds look insane. 1 planet in a trillion, with conditions just right for complex life to evolve. Some scientists disagree. They say the universe is huge. Trillions of stars, trillions of planets. Surely Earth can't be the only one. But here's the thing. We've scanned thousands of exoplanets. We've found hot Jupiters, super Earths, worlds made of ice. World is drowning in gas. But not one, not a single one, is an exact match for Earth. Maybe they're out there, just too far to see. Or maybe Earth really is a cosmic lottery ticket. And if that's true, it changes everything. Because life here isn't just lucky, it's fragile, unique, precious. It means that the oceans, the forests, the people walking this planet might be the rarest phenomenon the universe has ever produced. The rare Earth puzzle doesn't tell us we're alone. It tells us something deeper, that even if life exists elsewhere, it may never be quite like us, never on a planet quite like this. So, the next time you look around, at rivers, mountains, the night sky above, remember this: you might be standing on the most extraordinary place in the entire universe, the one in a trillion world we call home, the Big Bang. That's the story we all know. A hot, dense beginning, an expanding universe. But there's a catch. a big one. If the Big Bang happened the way we first imagined, the universe we see today should look messy, uneven, clumpy. Instead, it looks smooth, balanced, almost too perfect. That's where cosmic inflation enters the scene. Picture the universe, a fraction of a second after it began. Not seconds, not milliseconds. We're talking 10 menocubestas seconds. A time so early, so tiny, it's almost impossible to grasp. In that instant, the universe did something unbelievable. It didn't just expand, it exploded in size, faster than the speed of light. How fast? In less than the blink of an eye, something smaller than an atom ballooned into something the size of galaxies. Sounds impossible, right? Nothing moves faster than light. Einstein told us that, and he was right. But here's the trick. It didn't matter moving through space. It was space itself expanding, and the rules say space can stretch as fast as it wants. Inflation explains a lot. Why does the universe look so smooth? Why it looked the same in every direction? Why galaxies could form in just the right way? It even predicts something wild. Tiny quantum fluctuations from that first moment got stretched out by inflation. Those tiny ripples, they became the seeds of stars, galaxies, and planets. Without them, no Milky Way, no Earth, no us. But here's the mystery. What caused inflation? What stopped it? Why did the universe go through this bizarre growth spurt? Physicists think there might have been a mysterious inflaton field. Is C1 changes into skiing round, not bros, a kind of cosmic fuel that drove inflation forward, then suddenly shut off. But we've never detected it. We don't even know if it's real. Some theories say inflation didn't just happen once. It might still be happening in other parts of reality. If that's true, our universe is just one bubble in an endless frothing sea of universes. That's right. Inflation might be the key to the multiverse. And yet, the evidence is slippery. We search the skies for traces of inflation, subtle patterns in the cosmic microwave background, B modes in the polarization of light, hints of those first quantum ripples. So far, no smoking gun, just clues, just whispers. But if we ever confirm it, we'll have an answer to one of the deepest riddles: why our universe looks the way it does. The inflation mystery tells us something profound, that the universe we see, the galaxies, the stars, the cosmic web itself, all of it, was born from a split-second miracle, faster than light, beyond imagination, a breath of expansion. That set the stage for everything. The question remains, was it a one-time event, or just one bubble popping in an infinite cosmic foam? Whatever the answer, inflation reminds us of this. The universe doesn't play small. It thinks in extremes, and sometimes the biggest secrets are hiding in the very first flicker of time. The universe is big, unimaginably big, but it's also balanced in a way that seems almost impossible. Scientists call it the flatness problem. So, what does that mean? Flat doesn't mean the universe is like a pancake. It's not about shaping the way we think of shapes. It's about geometry. The geometry of space itself. Picture 3 possible universes. One curved like a sphere. Travel far enough and you'd loop back around. 2 curved like a saddle. A universe that bends outward, stretching without end. 3 flat. No curve. No bending. Just perfectly balanced. Parallel lines stay parallel forever. Now, here's the weird part. When we look at the universe, when we measure light from the early cosmos, we see it's flat, almost perfectly flat. But that's shocking, because flatness is unstable. Like balancing a pencil on its tip, even the tiniest wobble, the smallest shift in density, should have made the universe curve wildly over billions of years. And yet, it didn't. It stayed balanced, as if tuned with unimaginable precision. How precise? At 1 second after the Big Bang, the density of the universe had to be right. Within 1 part in 100 trillion. That's like flipping a coin 100 trillion times. And it lands heads every single time. So, why isn't the universe a sphere? Why isn't it a saddle? Why is it flat? That's the flatness problem. Scientists first saw the clues in the cosmic microwave background, that faint afterglow of the Big Bang. When satellites mapped it in detail, the geometry screamed flatness, a cosmic razor's edge. Some say it's just luck, that we live in a freakishly perfect universe, but most physicists don't buy that. They think something deeper is at work. That's where inflation comes in. The theory we explored before. When the universe expanded faster than light, any initial curvature would have been stretched out, like blowing up a balloon so huge its surface feels flat. Inflation flattens everything, and that might explain why the universe looks so perfectly balanced today. But here's the twist. Even if inflation explains the flatness, it raises new mysteries. What triggered inflation? Why did it end exactly when it did? Why does the density of the cosmos still cling so tightly to critical balance? It's as if the universe knew that life would someday need a stable, flat stage to evolve upon. Because if it were curved too much, galaxies wouldn't form, stars wouldn't ignite, planets wouldn't settle into steady orbits. No balance, no order, no us. The flatness problem isn't just a math riddle, it's a cosmic fine-tuning puzzle, the kind that makes us ask whether there's some hidden principle guiding the universe, or whether we just got unbelievably lucky. Maybe the flatness problem is pointing us to physics we haven't discovered yet, a deeper layer of reality, a rule of the cosmos we don't yet understand. Until then, all we can do is marvel. The universe didn't tip, didn't collapse, didn't spiral out of balance. It walked a perfect line, a razor's edge, and on that edge, everything we know, everything we love, everything we are, was able to exist. Look around. The stars, the galaxies, the planets, the people. It almost feels intentional, like the universe is set up just right, not too chaotic, not too empty, but balanced, as if tuned for life. This is the fine-tuning puzzle. Here's the heart of it. The laws of physics, the constants of nature. They could have been different. Masses of particles, strength of gravity, the speed of light, all numbers, all seemingly arbitrary, but they're not random. They sit in an astonishingly narrow range. Change them just a little, and the universe collapses, or never even begins. Gravity. If it were slightly stronger, stars would burn too fast, planets would fall inward. No stable life. If it were weaker, galaxies would never form. The universe would be a cold mist. No stars, no suns, no us. The strong nuclear force. It binds protons and neutrons together, but tweak it by 2%. And hydrogen never fuses. No carbon, no oxygen, no life. The cosmological constant, that mysterious dark energy. If it were just a fraction larger, space would rip apart before galaxies could form. If smaller, the universe would collapse back in. Even the ratio of matter to antimatter, out of balance by the tiniest fraction, and the universe would have annihilated itself before the first atom. Everywhere we look, nature seems balanced on a knife's edge, fine-tuned, delicately poised, as if the cosmos were rigged to allow stars, planets, and living things. So, the question is, why? Is it luck? The biggest cosmic coincidence of all time? That feels unsatisfying. Is it a necessity? Some hidden law that demands these numbers take the values they do? That's possible, but we haven't found it yet. Or is it selection? the multiverse idea, infinite universes, each with different physical laws, and we just happen to be in the rare one, where conditions allowed observers to exist. It sounds bold, but many physicists take it seriously, because it explains the fine-tuning without requiring luck or purpose. If enough universes exist, at least one had to come out just right. Still, that explanation doesn't erase the wonder. Why should a universe capable of life exist at all? Why not nothing? The fine-tuning puzzle isn't just science. It's philosophy. It's almost spiritual. It forces us to ask, is the universe indifferent? Or is there meaning woven into its fabric? Maybe the fine-tuning isn't about life in general. Maybe it's about complexity, the conditions that allow stars to burn and atoms to link. Also, allow galaxies to grow and planets to form. And once you have complexity, life becomes possible. So perhaps we are not the goal, we are just the consequence, an echo of cosmic math. And yet, standing here, aware of it all, we can't help but feel like the universe conspired to make this moment happen. The fine-tuning puzzle remains one of the deepest mysteries: luck, law, or multiverse. Each answer feels incomplete, but one thing is certain: the universe is balanced with breathtaking precision, balanced enough for galaxies, for stars, for Earth, for you, for me, and maybe that's the biggest mystery of all. What if this universe isn't the only one? What if ours is just one page in an infinite cosmic library? That's the multiverse hypothesis. The idea is simple. There isn't just one universe. There could be many, maybe infinite. Each has its own laws, its own physics, its own story. Some universes might look like ours: galaxies, stars, planets, life. Others could be bizarre: no matter, no time, different forces, different dimensions, worlds beyond imagination. Why take this wild idea seriously? Because the math almost demands it. Quantum mechanics, inflation theory, string theory, all hint at multiple universes. Let's break it down. Quantum worlds. In quantum physics, particles exist in probabilities. A cat can be alive and dead at once. Every outcome is possible. Some physicists argue, when a quantum decision happens, the universe splits. One version where event A occurs, another where event B occurs. Branching realities, endless copies. That's the many worlds interpretation. A multiverse born from quantum choice. Cosmic inflation. After the Big Bang, the universe expanded faster than light. But inflation might not have stopped everywhere. Some regions kept growing. Each bubble became its own universe. Separate, disconnected, a cosmic foam of infinite bubbles. That's the bubble multiverse. String theory. This mathematical framework suggests hidden dimensions. If true, the landscape of possible universes is vast. Each has different constants, different rules, billions upon billions of possible realities. So, the multiverse isn't just fantasy. It's a serious possibility, and it explains one big mystery: fine-tuning. Why are the laws of physics so perfectly balanced for life? If infinite universes exist, then, by chance, one had to be just right. We live in that one because we could not exist in the others. It sounds neat, but it raises new questions. Can we ever prove it? If other universes exist, they're outside our cosmic horizon. We can't see them, can't touch them, maybe never will. Some say we might find indirect hints. Collisions between universes could leave scars in the cosmic microwave background. Strange cold spots, anomalies in the sky, possible fingerprints of other worlds. But right now, it's speculation. Beautiful, seductive, but unconfirmed. Still, the implications are huge. If infinite universes exist, there could be infinite versions of you. A universe where you made a different choice. A universe where Earth never formed. A universe where life evolved in unrecognizable ways. It stretches the imagination. It challenges identity. Are we unique or one of countless echoes? The multiverse hypothesis pushes science to its limits. It blurs the line between physics and philosophy. Maybe it's real, maybe it's not. But the very possibility changes how we see everything. Because if the multiverse exists, then our universe, with its stars and galaxies, its people and mysteries, is not the whole story. It's just one chapter in an infinite cosmic library. And that might be the most mysterious idea of all. The universe has a story. It began with the Big Bang. It has expanded for nearly 14 billion years. Galaxies formed. Stars lit up. Life appeared. But what about the ending? How does this cosmic story close? Scientists imagine several possibilities. Each one is dramatic. Each one terrifying. Or strangely beautiful. Let's explore the great scenarios of cosmic fate. Heat, death, the most widely accepted ending, also called the Big Freeze. Here's the idea. The universe keeps expanding. Galaxies drift farther apart. Stars burn their last fuel. One by one, they die. New stars stop forming. Planets freeze. Black holes dominate. But even they evaporate. Through Hawking radiation, what's left? Nothing but cold particles, spread thin across infinite space. No energy gradients, no usable heat, no processes, maximum entropy, absolute stillness, a universe in perfect balance, but utterly dead. It's not sudden, it's not violent, it's slow, inevitable, a whisper of an ending. The Big Rip, a darker vision. This depends on dark energy. Right now, dark energy pushes the universe apart. But what if it grows stronger? Expansion would accelerate, without limit. Galaxies would tear away from each other. Then solar systems. Then planets. Then molecules. Even atoms themselves would rip apart. Spacetime shredded. The universe is literally torn to pieces. This is the Big Rip. A violent, catastrophic death. Every structure destroyed. Every particle is isolated. Nothing survives. The timeline? Tens of billions of years. Or sooner, if dark energy changes. A chilling thought. The fabric of reality may not hold forever. Rebirth, the Big Crunch. A more hopeful ending. Or at least, a cyclical one. What if expansion slows? What if gravity wins? Galaxies stop drifting apart. They begin to fall inward. The universe contracts. Stars collide. Black holes merge. Heat rises. Everything collapses into a fiery singularity, a mirror of the Big Bang. And from that collapse, maybe another explosion, a new universe is born. The cycle begins again. Bang, expansion, collapse, rebirth, an eternal cosmic heartbeat, the Big Crunch leading to the next Big Bang. Some call this the oscillating universe, forever beginning, forever ending, forever reborn. Which scenario is right? We don't know. Cosmology is still searching. Right now, data suggests expansion is accelerating. That leans toward heat death, or Big Rip. But the universe still holds mysteries. Dark energy is unknown. New physics may rewrite the ending. And maybe, just maybe, the cosmos never ends. Perhaps it transforms. Perhaps it recycles. Perhaps we've misunderstood the very nature of time. Here's the wonder. We're alive now, in this moment, in a brief, shining window when stars burn bright, and galaxies still dance. Billions of years from now, no one may remain to ask these questions, but we can. And that's extraordinary. The fate of the universe is written in its physics, but the mystery The beauty is that the story is still unfolding. Heat death, Big Rip, or rebirth. 3 endings, 3 visions of forever. Which one will it be? The cosmos holds the answer. We're just trying to read it. Black holes are strange. They bend space, they trap light, they warp time, but their strangest feature? They challenge the very laws of physics. This is where the information paradox begins. Imagine throwing a book into a black hole. Every word, every sentence, gone. The event horizon swallows it. No chance of recovery. But here's the problem. Physics says information can't be destroyed. Quantum mechanics insists that every detail of a system must remain encoded somewhere. Energy can change. Matter can change. But information, it should last forever. Black holes seem to disagree. They appear to delete information permanently. And that's a cosmic crime. Stephen Hawking raised the alarm. In the 1970s, he showed that black holes radiate, not endlessly stable, not eternal prisons, but slowly evaporating objects. We call it Hawking radiation. Particles escape. The black hole shrinks. Over time, it disappears. Here's the terrifying twist. If it vanishes completely, what happens to the information inside? Is it lost forever? Hawking's math suggested yes. Information destroyed. A violation of physics itself. This is the paradox. Physicists fought back. Some said the information hides in the radiation. Subtle patterns, impossible to detect now, but encoded in the quantum fuzz. Others proposed information gets smeared on the event horizon, a kind of cosmic hologram. The surface remembers what the inside swallows. This idea birthed the holographic principle, the wild suggestion that our 3-dimensional world may itself be a projection from a deeper 2-dimensional layer, a mind-bending fix for a universe that refuses to delete its history. But the debate rages on. Where does information go? Does the black hole hide it? Scramble it? Release it? Or truly destroy it? In 2019, new models suggested firewalls of energy at the horizon, a brutal zone where physics breaks, not smooth, not gentle, but violent. If true, it means falling into a black hole is even worse than we imagined. The stakes are enormous, because information isn't just about books, or atoms, or stars. It's about reality itself. The laws of physics are built on the conservation of information. If black holes can erase it, then our understanding the universe is broken. It would mean the future isn't predictable. The past isn't recoverable. The very script of the cosmos can be deleted. And yet, there's beauty in the paradox. Because paradoxes push science forward, they force us to rethink, to refine, to rebuild. Maybe black holes aren't cosmic erasers. Maybe they're cosmic libraries, storing information in ways we barely understand. Or maybe the universe itself. It is one vast hologram, every bit of data etched into space-time forever. So here we are, caught between destruction and preservation, between paradox and principle. Does the universe delete information, or does it just hide it? Where we haven't learned to look, the mystery remains, and until we solve it, the black hole laughs, keeping its secrets. At the edge of forever, open your eyes, look around. The world feels solid, stable, independent of you, but physics whispers something strange. Maybe reality doesn't fully exist until you observe it. Enter quantum mechanics, the strangest science we know. In the quantum world, particles behave like probabilities. Not here, not there, but everywhere at once. A wave of possibilities, a blur of maybes. Until we look, until we measure, then the wave collapses. The particle chooses a position. Observation doesn't just reveal reality, it creates it. The most famous proof? The double slit experiment. Fire electrons at two slits. If no one looks, they interfere like waves. They behave as if each electron goes through both slits at once. But the moment you observe, the wave vanishes. Electrons act like tiny bullets. They pick one slit. They leave a clean pattern. Observation changes the outcome. Reality bends to the act of looking. That leads to a haunting question. Does the universe exist when no one's watching? Is the moon still there when no one sees it? Einstein hated this idea. He famously asked, "Does the moon exist only when I look at it?" Most physicists say reality is objective. It doesn't need us. But quantum mechanics doesn't let us off that easily. Some argue for the Copenhagen interpretation. The wave function collapses only when observed. The act of looking creates certainty. Others push the many worlds interpretation. Nothing collapses. Instead, every possibility splits. All outcomes happen in parallel universes. We just witnessed one. And then there's the boldest thought of all. That consciousness itself plays a role. That reality depends, at some deep level, on minds to see it. If that's true, the cosmos isn't a cold machine. It's participatory. We aren't just passengers. We're co-creators. Reality and observer locked in a dance. No universe without us. No us without the universe. Of course, this might not be the final word. Future physics may untangle the paradox. We might discover the universe is real, solid, unchanging, observer or not. But until then, the mystery lingers. Maybe reality doesn't just exist. Maybe it waits, silent, hidden, until we dare to look. Imagine two particles, born together, linked in a way that defies common sense. Separate them, one on Earth, one across the galaxy. Touch one, and the other responds, instantly. No signal, no travel, no delay. Einstein hated it. He called it spooky action at a distance. This is quantum entanglement, a connection beyond space and time. Two particles, no matter how far apart, share the same quantum state. Measure one, and the other instantly knows. It's as if reality cheats. As if the cosmos whispers in secret code. Here's the kicker. Nothing is supposed to move faster than light. That's physics law, IFAD 1. The cosmic speed limit. Yet entanglement seems to laugh at that rule. It skips distance. It ignores speed. The result? Instant correlations across unimaginable space. But wait, does this mean faster than light communication? Could we send messages this way? Sadly, no. Entanglement shares correlations, not data. It's like rolling two dice on opposite ends of the universe, and always getting matching numbers. Spooky, yes, but no cheat code for faster than light texting. Still, the mystery remains. How does the universe pull this off? Some say it proves the universe is non-local. That space isn't as separate as it seems. Everything, at the deepest level, is connected. Others suggest hidden variables, rules we just don't know yet. Einstein hoped this was true, but experiments show otherwise. Quantum mechanics wins. The cosmos really is this weird. Entanglement isn't just a theory anymore, it's real technology. Quantum computers use it to process impossible calculations. Quantum cryptography uses it to create unbreakable codes. Even the dream of a quantum internet rides on entanglement's ghostly strings. What was once spooky is now the engine of tomorrow. And yet, the philosophical question bites harder. If two particles can talk instantly, what does that say about reality? Is space just an illusion? Is the universe more like one vast whole than a collection of separate parts? Entanglement might be telling us that division is an illusion, that at the deepest level, everything is one, The mystery stands. Einstein resisted it. Physicists wrestle with it. And philosophers marvel at it. Entanglement is the closest thing we've found to magic hiding in science. A reminder that the universe is stranger than even our boldest imaginations. We stare at galaxies. We measure black holes. We map dark matter. But the strangest mystery of all, it isn't out there. It's in here. Consciousness. Awareness. The simple fact that you are experiencing this moment. Think about it. The universe is 13.8 billion years old. Stars exploded. Planets formed. Life crawled from oceans. And somehow, right now, you are listening, thinking, feeling. Why? Science can explain neurons. Electrochemical signals are firing in your brain. Circuits of flesh and electricity. But here's the puzzle. Why does that feel like anything? Why is there an inner movie? Why do we not just act, but also experience? This is called the hard problem of consciousness. Not how the brain works mechanically, but why does it feel like something to be you? Maybe it's an illusion. Some scientists argue consciousness isn't real. It's just the brain fooling itself, like a trick of the light. But if that's true, who's being fooled? An illusion still needs a witness. Others say consciousness is fundamental, like space, like time. It doesn't come from matter. It creates matter, a radical thought. That maybe the universe is conscious, and we are fragments of its awareness. Then there's the idea of emergence. That is when enough complexity arises, consciousness just switches on, like turning on a light bulb. But why this light? Why this awareness instead of endless darkness? Here's the real kicker. Without consciousness, all the mysteries of the universe mean nothing. Stars, galaxies, physics, laws, none of it matters if there's no one awake to wonder. In a way, consciousness is the universe looking back at itself, the cosmos dreaming through us. Technology is now poking at the edges. Neural implants, brain scans, artificial intelligence. Could a machine ever be conscious? Could awareness emerge in silicon the way it did in carbon? If it does, would we even know? How would we measure a thought? A feeling? A soul? This is why consciousness feels scarier than black holes or dark energy. Because it isn't out there. It's personal. It's immediate. It's you. The deepest mystery might not be the universe expanding. It might be the fact that you know you exist. The cosmos is vast, but the strangest frontier is sitting inside your skull. The question isn't just what consciousness is, it's why does it exist at all? And until we solve that, the greatest mystery of the universe might be the simple act of being aware. We've mapped stars, we've tracked black holes, we've measured cosmic radiation, and yet the universe still keeps secrets. Some questions might never have answers. Some mysteries are simply too big, too old, too far away. Take the edges of the cosmos. We see galaxies billions of light years away, but that light left them billions of years ago. We're seeing the past, not the present, and beyond that, we may never know. There could be regions of space that are forever out of reach, forever invisible. Then there's the quantum world, the tiniest scales of reality, where particles exist in multiple states, where observation changes outcomes. No matter how clever we get, some things might stay hidden. Nature doesn't have to answer our questions. Sometimes it just refuses. Even the universe itself may be limited. Theories suggest it could be infinite, or part of a multiverse, or governed by laws we haven't discovered. We might be forever confined to what our senses, our instruments, our mathematics can grasp. Time is another limit. We can only observe what exists now, or what light reveals from the past. We can't rewind or fast forward reality. We can't peek beyond the horizon of what is possible. And consciousness, the very thing pondering these limits, might be incapable of fully understanding itself. There may be truths that require a mind far beyond human capacity. Some mysteries are practical limits. Even if the universe reveals itself, we might never reach the knowledge. Distance, energy, and entropy place hard barriers. Others are philosophical. Even if we see, measure, calculate, can we truly know the essence of reality? Or are we always interpreting shadows on a cosmic wall? Science is a lantern. It lights the dark corners of the cosmos, but some corners remain pitch black. Some knowledge may be forever beyond reach. And that's okay. Mystery drives discovery. The questions we may never answer push us to look harder, think deeper, imagine beyond what is comfortable or convenient. The universe may keep secrets for a reason. It humbles us. It challenges us. It reminds us of our place. There are limits to what we know, and perhaps limits to what we can know. But reaching toward those limits, that's the adventure. That's the thrill of exploration. That's the heartbeat of human curiosity. The cosmos isn't finished with us, and we aren't finished with it. Some mysteries will remain, and maybe that's the point. The universe remembers. Every star, every galaxy, every photon tells a story. But what if that memory fades? What if the cosmic ledger erases itself? The universe is expanding, faster and faster. Galaxies drift apart like boats on an endless ocean. At first, we barely notice. Stars in our neighborhood still shine bright. Light still reaches our telescopes. But over billions of years, the story changes. Distances stretch. Light from distant galaxies struggles to reach us. Some light will never arrive. Their histories will vanish before our eyes. Imagine trying to read a book that's constantly dissolving into mist. The pages scatter, the words fade. That's the universe. The farther away a galaxy, the faster it disappears beyond our cosmic horizon. The universe is not cruel. It's inevitable. Dark energy drives the expansion. It pushes everything apart. It ensures that, in time, the memory of entire regions of space could be lost. Not just galaxies, not just stars. Even fundamental cosmic signals, cosmic background radiation, relics of the Big Bang will fade. Future astronomers, billions of years from now, may not even detect the universe's origin. The story of creation itself could become impossible to reconstruct. Think about it. All we know about the cosmos comes from signals reaching us. If signals can't reach, knowledge vanishes. History erodes. The universe becomes a silent, empty place. It's not just distant galaxies at risk. Over incomprehensible timescales, even local structures may drift apart. The Milky Way, Andromeda, and other galactic neighbors, some could vanish beyond the horizon. Entire chapters of the cosmic saga could be lost. This raises a profound question. Is memory only tied to observation? Does the universe exist differently if we can't witness it? Some physicists warn, cosmic expansion might erase not just light, but evidence of past events. Future civilizations may see a barren sky, oblivious to the rich history we uncover today. Our knowledge is fleeting. The universe isn't static. It's dynamic, expanding, forgetting. We are witnesses in a brief window. When cosmic memory is still accessible, there's beauty in this fragility. It reminds us that observation is precious. It urges us to study, explore, and record, because the cosmos might not wait forever. The expansion of space isn't just a mystery of distance, it's a mystery of memory. A reminder that history itself can vanish, and that every discovery we make today is a treasure against the tide of forgetting. The universe may eventually erase itself, but for now, the story continues, and we are its scribes. After traveling across the cosmos, after chasing dark matter and dark energy, peering into black holes, and pondering the fate of galaxies, we reach the final reflection. We are the mystery. The universe is vast, ancient, and unknowable. Billions of galaxies, trillions of stars, and countless planets spin in silent orbits. Yet here we are, tiny, fragile, conscious, able to wonder, able to question, able to explore. Humanity is both seeker and secret. We chase answers across the stars, yet some mysteries live inside us. Consciousness, time, memory, our ability to perceive and reflect. These may be the universe's most confounding puzzles. Every discovery reveals another question. Every cosmic horizon we reach pushes the edge of the unknown further away. We are explorers, mapping not only the stars, but ourselves. Look at the night sky. Every speck of light is a story. Every galaxy is a city of suns. Every photon is a messenger from the past. Yet in the grand scheme, our existence is fleeting. Our planet, a single dot in a cosmic ocean. And yet, paradoxically, our curiosity makes us mighty. The universe may be infinite, but our imagination bridges the gap. We can think beyond our sun, beyond our Milky Way, beyond even the edge of time itself. We are the universe asking questions about itself. We are stardust made self-aware. Each thought, each observation, each discovery is a glimpse of the cosmic mind. This is both humbling and empowering. We may never know everything. We may never witness the birth of the first stars or the ultimate fate of the cosmos. But in our pursuit, we define ourselves. We transform ignorance into knowledge, mystery into curiosity, the unknown into wonder. So, what is the most mysterious thing in the universe? Perhaps it's not a black hole, a quasar, or dark energy. Perhaps it's us, the observers, the thinkers, the dreamers, the beings capable of asking the very questions that the cosmos itself cannot answer. And that is why we look up. That is why we explore. That is why we keep asking. The universe is a puzzle, and we are part of the solution and the riddle. We are the bridge between the cosmos and comprehension. The mystery of the universe is inseparable from our own mystery. So, let's continue seeking, learning, and wondering, because while the universe holds its secrets tight, our curiosity is boundless. If this journey through cosmic mysteries inspired you, subscribe now and keep exploring with us. The universe is waiting, and so are we.